Assalamualaikum and hi everyone. So today we will present Poynting theorem. So we are from group 9 for the electromagnetic EEE 3130. So the first one of the member is Muhammad Imam Biwandau, that is me. The next one we have Siti Fazlina binti Muhammad Ridwan, Numanul Mujahid bin Mat Yusof, Hazirun Mustaqim bin Muhammad Kasim, Nalan anak lelaki Subramaniam, Jeremy Jais, anak Michael, and the last one is Tarmis, anak lelaki Tamil Selvan. So, we will start our program today with the history of Poynting theorem. Let's go.
Hi, my name is Jeremy Jais Anna Michael, and my metric number is 203133, and I'm going to explain a little bit about the background and the history behind this Poynting theorem. In electrodynamics, Poynting's theorem is a statement of conservation of energy for the electromagnetic field in the form of partial differential equation developed by British physicist John Henry Poynting. And from this, we can know that this Poynting's theorem is developed by John Henry Poynting. And Poynting's theorem is analogous to the work energy theorem in classical mechanics and mathematically similar to the continuity equation because it relates the energy stored in the electromagnetic field to the work done on charge distribution. Example, electrically charged object through energy flux. And right now I'm going to explain a little bit of background about John Henry Poynting, which is the one who developed this Poynting's theorem, the theorem that we are going to learn throughout this video, which is Poynting's theorem. So John Henry Poynting, he was born on September 9th, 1852 and died on 30th of March, 1914. He was an English physicist. He was the first professor of physics at Mason Science College throughout the 1880 to the 1900s, and then the successor of institution, the University of Birmingham, until his death. Poynting was the youngest son of Thomas Alva Poynting, a Unitarian minister. He was born at the parsonage of the Mountain Unitarian Chapel in Eccles in Lancashire. In his boyhood, he was educated in the nearby school, and then he attended Owens College and then University of Manchester, where his physics teachers included Osborne Reynolds and the great Balfour Stewart. And then from 1872 to 1876, he was a student at Cambridge, where he attained high honors in mathematics after taking Rhines with Edward Roth. In the late 1870s, he worked in the Cavendish Laboratory in Cambridge under James Clerk Maxwell. In 1880, he became the first professor of physics at the University of Birmingham, and he was the developer and eponym of the Poynting vector or the Poynting theorem, which is the theorem we are going to learn throughout this video. And Poynting vector, which describes the direction and magnitude of electromagnetic energy flow and is used in the Poynting theorem, a statement about energy conservation for electric and magnetic fields. This work was first published in 1884. He performed a measurement of Newton's gravitational constant by innovative means during 1893. In 1903, he was the first to realize that the sun's radiation can draw in small particles towards it. This was later named the Poynting-Robertson effect. And that's all for the background and the history that we all should know about Poynting theorem.
Assalamualaikum and a very good day. My name is Siti Fazlina binti Muhammad Ridwan with the magic number 191914. Today I will be presenting about the definition of Poynting theorem and Poynting vector, which is a topic that is being chosen by my group Group 9 in the course Basic Electromagnetism. So without further ado, let's get into it. So first of all, let us talk about what is electromagnetic waves and what does it do. So generally, electromagnetic waves are the vibration that occurs in between electric and magnetic fields. We can take light as an example of electromagnetic waves. And since light is an EM wave, it is able to transport energy and deliver it on any object that it falls on. Poynting theorem, which is one of the many electromagnetism theorem, is related directly and closely to this concept. So therefore, in this presentation, I will further explain on what is Poynting vector. Generally, Poynting vector is the rate of energy transfer or transport per unit area. It can be shown by a capital S, which is either bolded or being written an arrow on top of the letter S to emphasize that it is a vector and has direction. The magnitude of the Poynting vector can be explained by this general equation that you can see here, where we can actually understand that Poynting vector is the rate of energy transported per unit area. And since the rate of energy is equals to power, the size of the Poynting vector is nothing but the instantaneous power divided by the area. Finally, this gives Poynting vector the SI unit of watts per square meter. Okay, so now I will be explaining about the mathematical equation. So in general mathematical terms, the equation of the Poynting vector is again bolded S, or being drawn an arrow above the letter S, equals to 1 over mu naught E times B, or E cross B. As we can see from equation, E and B is a cross product, which is a way of multiplying two vectors. So we can see that Poynting vector is the magnitude of the first vector, E, times by the magnitude of the second vector, B, times by sine theta, where theta is the angle in between E and B. For electrical and magnetic field, the angle between them is perpendicular or equals to 90 degrees. Since sine times 90 degrees is equals to 1, the size of the Poynting vector S is actually E times B at any moment. And again, Poynting vector is a cross product, making it having direction. In order to find the direction of the Poynting vector, we can use the right hand rule, where we can use the 3 fingers on our right hand, which is our middle finger, our index finger, and our thumb. The thumb represents the z-axis, the middle represents the y-axis, and the index finger represents the x-axis. In this way, we are able to determine the direction easily. For an example, if we put our index finger and point it at the direction of E, which is upwards, and we point our middle finger towards the direction of B, this will be the S, or the Poynting vector. So this is where the wave is traveling.
I'm Alan Subramaniam. My text number is 202738. Good afternoon, everyone. Today I'm going to present the example question of Poynting theorem. So I would share screen in a while, and let's begin with our presentation. All right, okay. So this is the example of question, and the topic is Poynting theorem. Okay, so the expression says that H field of the plane wave propagating in free space is given by the expression below. So you can see H equals to 5 square root 3 over eta naught cos, and then in the x-axis, and then the y-axis, the entire expression you can read below. Okay. So now the main problem of this is to find the time average power flow density. So now we're going to talk about how we're going to solve this problem, and all the working below has been stated more clearly. Okay. So as you can see, H is the magnetic field. The magnetic field can it propagates in x-axis and y-axis. So as you can see in the arrow on the right of the average power flow density, h x on the right, hy is on the up, and then in the middle is the resultant magnetic field. Okay, so here we go that hx is the magnetic field in the x-axis, equals to 5 square root 3 over eta naught. So that you just take from the x-axis equation, and then the hy would be the same. You just take the front of 5 over naught eta naught. Okay, then the resultant magnetic field is equals to the square root of hx plus hy square, and then the square root it, and then you just sub in the value that you state above there, and then the final answer of the ht is 10 over eta naught. Okay, so now let's go to the point. For us to derive the equation of the power density, the main equation, the formula is h naught square over 2 eta, and then on the side note I've stated E naught over H naught equals to eta naught. So you just represent in terms of E naught equals to eta naught H naught, and then you just sub in the actual formula above there. And then when you derive the equation you will get is n eta naught H naught square over 2. Okay, then let's go below. As you can see the P average equals to eta naught times 10 over eta naught square. Because I've already in the so work it's square and plus you get T over eta. So that's the answer of the question. Very much. I'm done. Okay.
Hi, so with me again in the Poynting theorem application. Let's go. Okay, we can see here is a long solenoidal inductor application. So the first one is the 19th formula is the magnetic field intensity, where we can see the I is denoted as KD. The formula is magnetic field intensity equal to I over D in the vector of Iz. So down there in the equation number 20 is the equation of electric field with the sum of a conservative homogeneous part, that is EH. Okay, the figure is actually a one-turn solenoid surrounded with a volume of a surface S. So this surface is denoted by the dashed line. So we want to find the Poynting flux through the surface. So we can consider using this formula that S equal to E cross H. So S is the Poynting vector we can use, and the EH is from the previous vector we found. So with this formula, we can see that we can find the Poynting flux. So when we derive the formula, so we can say that the integral of E and H, E cross H, so we can get approximately L, the inductor formula down there, the mu naught pi A squared over D. So from that, we can also use the evaluation of the right hand side of the formula number 8 that is used to store magnetic energy. So when we use that, we also get the same equation. So this is validating the quasi-static approximation. So we can see that then we comparing the magnetic energy, we are neglecting the electric energy storage. because we are only interested in the magnitude comparison, and we know that the homogeneous solution is proportional to the particular solution. So we can conclude that the magneto-quasi-static approximation is valid, that we provide the angular frequency is small compared to the time required of an electromagnetic wave to propagate to the radius of the solenoid. Okay, what is MQS? The MQS is the magneto-quasi-static. Let's see what is magneto-quasi-static. The magneto-quasi-static field is a class of electromagnetic field actually, which is a slow oscillating magnetic field. The magneto-quasi-static field is typically generated by a low frequency induction from a magnetic dipole or a current load. The magnetic near fields of such an emitter behave differently from the more commonly used far field, that is electromagnetic radiation. That's all for the application.
As mentioned before, Poynting's theorem is a statement of conservation of energy for the electromagnetic field. It involves the energy stored in the electromagnetic field and the work done charge distribution. As we all know, the electromagnetic energy can be transferred, stored in either a magnetic or electric field, and dissipated. Poynting's theorem is able to relate these properties. There are many applications of Poynting's theorem. One example is a capacitor. As I mentioned, one of the properties that the theorem relates is the storage of electromagnetic energy in electric field. A parallel plate capacitor utilizes this property as it stores energy in the electric field between two plates of opposite polarity. This happens as opposite charges accumulate in each of the plates. They are separated by a dielectric material, thus creating an electric field that stores the energy. The operation of a capacitor involves Poynting's theorem.
Assalamualaikum warahmatullahi wabarakatuh. My name is Numanu Mujahid by myself, and today we going to explain on the Poynting's theorem equation. So, as has been stated before, Poynting's theorem states that the net power flowing out of a given volume V is equal to the rate of decrease in the energy stored within V minus the ohmic losses. So now we can see from this image, this is volume V, this is V, and there is power going in and there's also power going out. So the total of power going out of volume V is equal to the rate of decrease in the energy in electric field and energy in magnetic field minus the ohmic losses. So we can also interpret the ohmic losses as the ohmic power dissipated. Next, we're going to look at the Poynting's theorem equation. The Poynting's theorem equation is surface integral E bar cross H bar dot ds bar equal negative dou over dou t volume integral of 1 over 2 epsilon E squared plus 1 over 2 mu H squared dV minus volume integral sigma E squared dV. So we are going to look at each of the term from this equation. So on the left side, there we have circle. So of surface integral E bar cross H bar dot ds bar is the total power leaving the volume. So negative dou over dou t is the rate of decrease. And this the middle one, volume integral 1 over 2 epsilon E squared plus 1 over 2 mu H squared dV is the energy stored in electric field and the magnetic field. And last one, negative volume integral sigma E squared dV is ohmic power dissipated. So on the next slide, we're going to look at the proof of the equation. So we can see that energy can be from one point to another point by means of electromagnetic wave. Rate of such energy transportation can be obtained from Maxwell equation. So there are two Maxwell equations. First one from Faraday's law, which is del cross E bar equal to negative mu dou H bar over dou T. The second one from Ampere's modified circuits law, which is del cross E bar equal to sigma E bar plus epsilon dou E bar over dou T. Taking the dot product from equation 2, this E bar gives E bar dot del cross H bar equal to E bar dot sigma E bar plus epsilon dou E bar over dou T. And further simplifying that, got E bar dot del cross H bar equal to sigma E squared plus E bar dot epsilon dou E bar over dou T. But for any vector field, A bar and B bar is del dot A bar cross B bar equal to B bar dot del cross A bar minus A bar dot del cross B bar. Moving this part to the left, del dot A bar cross B bar plus A bar dot del cross B bar equal to B bar dot del cross A bar. And letting A bar as H bar and B bar as E bar, and applying this to the above vector identity gives us del dot H bar cross E bar plus H bar dot del cross E bar equal to E bar dot del cross H bar. So this will be the third equation. But E bar dot del cross H bar equal to sigma E squared plus E bar dot epsilon dou E bar over dou T. And simplifying that, sigma E squared plus epsilon over 2 dou E bar over dou T. So this will be the fourth equation. Taking dot product on equation 1, which we have seen previous slide with H bar, gives H bar dot del cross E bar equal to H bar dot negative mu dou H bar over dou T, and simplifying that, negative mu over 2 dou H squared over dou T. So this will be the fifth equation. Next, substituting equation 4 and 5 in equation 3, we get negative del dot E bar cross H bar minus mu over 2 dou H squared over dou T equal to sigma E squared plus epsilon over 2 dou E squared over dou T. And by moving this term to the right side, we get negative del dot E bar cross H bar minus sigma E squared plus epsilon over 2 dou E squared over dou T plus mu over 2 dou H squared over dou T. And by removing the negative sign, you get del dot E bar cross H bar equal to negative sigma E squared minus epsilon over 2 dou E squared over dou T minus mu over 2 dou H squared over dou T. And by substituting equation 4 and 5, we get del dot E bar cross H bar equal to negative sigma E squared minus dou over dou T of 1 over 2 epsilon E squared plus 1 over 2 mu H squared. And by taking the volume integral on both sides, we get volume integral of del dot E bar cross H bar dot dV equal to negative dou over dou T volume integral of 1 over 2 epsilon E squared plus 1 over 2 mu H squared dV minus volume integral sigma E squared dV. And applying the divergence theorem on left side of this equation, we get volume integral del dot E bar cross H bar dot ds bar equal to negative dou over dou T volume integral of 1 over 2 epsilon E squared plus 1 over 2 mu H squared dV minus volume integral of sigma E squared dV. Hence, the net power flowing out of given volume V is equal to the rate of decrease of energy stored in electric and magnetic field within V and minus the ohmic losses. And that's how we prove the equation of the Poynting theorem. So apart from that, Poynting's theorem also says that the cross product of electrical field and magnetic field at any point is a measure of the rate of energy flow per unit area at that point. That is, P bar equal to E bar cross H bar watts per meter squared.
As a conclusion, in electrodynamics, Poynting's theorem is a statement of conservation of energy for the electromagnetic field in the form of a partial differential equation developed by British physicist John Henry Poynting. Poynting's theorem is analogous to the work energy theorem in classical mechanics and mathematically similar to the continuity equation, because it relates the energy stored in the electromagnetic field to the work done on a charge distribution through energy flux. What the Poynting theorem really says is that the time rate of change of the energy density of electromagnetic fields at a point is equal to the negative of the dispersion of the Poynting vector at that point. The energy flow at that point may be due solely to the movement of the fields carrying their energies with them. There may be no electromagnetic radiation at all involved. So I think that's all from us. Thank you.